In the early 1800s, new contributions to geometry finally emerged after thousands of years of studying just Euclid. However, it involved rejecting one of Euclid's five postulates, or statements that one must assume to be true, as a basis for geometry. Surprisingly, this rejection led to a new geometry that was fully consistent with itself. Let's take a closer look. Geometry existed according to the rules of Euclid for millennia. It had gone largely unquestioned during that entire time period, aside from one small problem: the parallel postulate. It kind of stuck out like a sore thumb compared to the other four postulates, and mathematicians for years thought that there must be some way to prove it. It wasn't until the 19th century when mathematicians realized they could work with the negation of the parallel postulate, which would say that through a point not on the line, multiple parallels exist instead of only one, which Euclid said. They found that using this negation along with the other four postulates, they could create a whole new geometry. This geometry became known as hyperbolic geometry and can be described by a surface of constant negative curvature. However, a surface like this becomes really hard to work with, so our solution is to just project the entire hyperbolic surface onto a two-dimensional Euclidean circle. We now call this the Poincare Disk, named after French mathematician Henri Poincare, who utilized it in his study of non-Euclidean geometry. The Poincare disk has the unique property that 2 points of some Euclidean distance apart will have a longer hyperbolic distance the farther away from the center they are. The limiting case would be any point on the boundary, because the boundary is considered to be an infinite distance away from the center. Thus, the boundary is not technically considered to be a part of the hyperbolic space, although it is very useful in helping us make constructions. In fact, another interesting property is that all hyperbolic lines must either be diameters of the circle or be portions of Euclidean circles constructed orthogonal to that boundary. This makes it easy to see that any triangle in hyperbolic space must have an angle sum of less than 180 degrees. Taking advantage of the negative curvature, it is even possible to draw hexagons which are composed entirely of right angles. There are many more curiosities and properties that exist, but those go beyond the scope of this video. I hope this video provided a nice introduction to hyperbolic geometry using the Poincare disk model and sparks curiosity for you to learn more. That's all for now. I will see you in the next video, which will be the finale.